This is going to be a deep dive into psychrometrics. So we're not just going to look at psych charts and how those work, but also how all the values in those psych charts are calculated and derived. I think knowing that gives you a good fundamental understanding of not just what those properties are, but also processes to go from one state to another state. So let's dive in and we can see how we do that and how it's used. Like I said, goal is to get a better fundamental understanding of psychrometrics and knowing properties of moist air, knowing how to solve for them numerically rather than relying on charts, and then looking at how to apply those to real processes and things that you'll find in real life and in plants. So psychrometrics is the study of thermodynamic properties of air and vapor mixtures. Air you think of as basically nitrogen and oxygen, where it's 78% nitrogen, 21% O2, and then something like a percent of trace gases like argon, CO2, and water vapor. It's a really small amount of those trace gases, but the amount of water vapor in it affects the thermodynamic properties of it pretty significantly. So that's why we have to factor that in when we're doing any type of air analysis. So for HVAC or cooling towers or things like that. And the amount of water vapor in the air varies all the time if you're looking at outside air. So you can't just use a lookup table. You typically use a psychrometric chart if you're going to do any kind of lookups. So let's get into what psychrometric charts are. You may have seen this. If you haven't, don't worry about it too much right now, but basically what you have is on the x-axis, you've got dry bulb temperature. So as you move left to right, your air is getting hotter. And as you go vertically, your humidity ratio is getting higher. Humidity ratio is the ratio of the mass of water vapor in the air to the mass of dry air. So basically what this chart is you're finding the intersection of your temperature and humidity ratio, and that tells you what state your air is in. And if you know the state of air you're at, then you can find other properties of that air as well. So there are these parabolic looking curves are for constant relative humidity, which means if my relative humidity is constant, this is how my temperature, and my temperature changes, this is how my humidity ratio would have to change with it. These curves, as relative humidity increases, these curves move kind of up and to the left until you get to this one on the far left here, which is the saturation curve. When air is saturated, that means it can no longer hold any more water vapor. The amount of water vapor it can hold is a function of its temperature. So as air gets hotter, it can hold more water vapor. And if you were to try to evaporate or inject any more gas water vapor into an air mixture that's already saturated, any additional water vapor gas would start to condense into a liquid at this saturation point. That's all we're going to talk about for now, but we'll dive deeper later. I guess one last thing I'll point out is the usefulness of the psychrometric chart is that if you know any two properties, so not just temperature and humidity ratio, but say you know humidity ratio and relative humidity, you can find where the two values intersect, and then you can infer what all the other properties of air are. So if I've got 60% relative humidity and a humidity ratio of whatever this value is, I can find that I'm here on the psychrometric chart. So therefore my temperature is this temperature, and my enthalpy is, if I were to follow this line that slopes down into to the right, follow your enthalpy line, that's your enthalpy. And you can also do the same thing to find what your wet bulb temp is. So point is, if you know two values, you can get everything else. The psych chart's also useful, not just if you know one property or one state of air that you're at, but if you know two of them. So say I've got one here and one here, I can visualize what has to happen to that air to get to that point by looking at this kind of key here. So if I'm moving from left to right, I'm heating, right to left is cooling. Down, if I'm moving up vertically, I'm humidifying, and down is dehumidifying. But also any type of diagonal process is going to be a combination of the two. So let's say I've got an air point that's, say, right in the middle of this set of arrows here, and I want to end up here. I know that I have to heat and humidify the air to get to that point. Or for another example, let's say I want to end up down here. I need to move down and to the left. That means I need to cool it and dehumidify it. So knowing two states tells you kind of the process you need to take to get there. So why do we not just rely on charts? Why do we have to do numerical calculations? For one, let's say you've got thousands and thousands of rows of data where you know two properties of air and you need to calculate a third. You can't reference a psychrometric chart that many times. You need to be able to calculate those yourself. Also, a psychrometric chart, something I didn't say, is that these are for atmospheric pressure typically. So this is if you're at sea level. If you were to have a different, if you're at a different elevation, so say you're in Denver and you're 5,000 feet up, and that's a different atmospheric air pressure, you would have a different psychrometric chart. The shape of all the curves and all it would look basically the same, but the values would be different. So if you've got thousands of rows of data again, and you've got different air pressures, or if you've at a pressure where it's not easy to find a psychrometric chart for your conditions, then it's really useful to be able to use pressure as a function of whatever you're trying to find rather than analyzing a psychrometric chart that might be hard to get your hands on. Same thing for compressed air. I don't think I've ever seen a compressed air psych chart, but you can apply these to compressed air. And then last is if you're doing any kind of analysis on ultra dry air, so something with very low humidity ratio. Let's say you're all the way down here in your humidity ratio and you want to find some properties of that air. If you were to then try to find where that intersects your saturation curve, psych charts don't go over that far. So if you're trying to analyze super dry air like compressed air after a desiccant dryer, for example, you're going to be out of luck with a psych chart and you need to be able to calculate that stuff by hand. So we have Excel add-ins and macros that do that for us, but understanding how those work is important. When we talk about knowing two properties of air and then finding where they intersect on a psych chart and then figuring out what the rest of them are from that, these are the properties we're typically talking about right here. I won't read them off, but because we're going to talk about them all in a minute here individually. But generally, these 8 properties are what we're either trying to find or we have these as inputs to try to find another one. And the whole point of this is that we don't need a psychrometric chart. We can derive these and calculate them ourselves as long as we know 3 fundamental concepts, which we'll get into now. Those 3 things are the ideal gas law, Dalton's law of partial pressures, and then being able to calculate saturated steam properties as a function of pressure or temperature. So if I know a temperature, what's my saturated steam pressure, and vice versa. As long as we know these 3 things, then we can calculate all psychrometric properties. Start with the ideal gas law. In chemistry, you probably learned PV equals nRT, so pressure times volume equals moles times universal gas constant times absolute temperature. That holds true for an ideal gas. Generally, there's no such thing as an ideal gas, but this is a really good approximation for what you see in real life. My issue with this is in here, or moles. We never measure moles in the field. You've never talked about moles per minute if you're talking about airflow. It's always mass flow. So what you can do, though, is modify this a little bit to this guy right here. Now it's really useful if you have PV equals mRT, where m is mass, and then R, instead of being the universal gas constant that applies to any gas, you have a specific gas constant. And the way you get a specific gas constant is you take universal gas constant divided by molar mass. So if we're doing imperial units, take 1545 divided by the molar mass of the gas you're dealing with. So for air, it's 28.96. Sorry, for dry air, it's 28.96. That's the molar mass. And if you take your 1545 divided by molar mass, you get 53.35 is the specific gas constant. Your specific gas constant for water vapor is if you divide by 18.02, then you get this for your specific gas constant. The units for 1545 are pound force feet per mole times degree Rankine. Just remember 1545 and you'll be good. The molar mass is what you see in a periodic table, so it's grams per mole, which is the same thing as pound mass per pound mole. So if you just do 1545 divided by the periodic table mass, then you're going to be good to go. And then M is going to be pound mass. You don't have to worry about slugs or anything for this. Quick example, if you've got a box that's a cubic foot in volume and you're at atmospheric pressure inside that box, the temperature is 70 degrees in there, how do you find the mass of air in that box? Simply do your ideal gas law, so PV equals MRT. P is going to be in pounds per square foot, so take your PSI and multiply by 144 to get into pounds per square foot, times cubic feet equals mass, which is what we're trying to solve for, times specific gas constant for dry air, which is R, times T. You got to use absolute temperature, so you add 460 to your Fahrenheit to get degrees Rankine. Do that, you end up, for this specific problem, you end up with about 0.075 pounds, which happens to be the density of dry air roughly at specific, or at standard conditions. I think standard conditions is 68 degrees, depending on whatever your reference is. But that's one way to apply the ideal gas law. You can do the same thing for metric. I'm going to gloss over that because we do imperial mostly. Next is Dalton's law. What Dalton's law says is that if you've got a mixture of different gases, the total pressure of that gas is going to be comprised of the sum of the partial pressures of each gas. In other words, if I've got air, which is nitrogen and oxygen and water vapor, and it's some total pressure like 14.7 or whatever, that 14.7 or whatever the total pressure is going to be equal to the pressure from your dry air plus the pressure from your water vapor. Each one contributes a little bit of the pressure and they add up to the total. And the amount of each individual gas's contribution to the total pressure is proportional to the amount of moles in that gas mixture. So the pressure ratio, or the ratio of your partial pressure of some gas to the total pressure, is going to be equal to the moles of that gas in the mixture divided by the total moles. I mentioned earlier that I don't like using moles because we never measure that actually. So when we get into calculations, there's going to be some molar mass conversion factors here, but this is fundamentally what this equation or what this principle is saying. Here's another quick example. So if you've got that same box that's a cubic foot, you shut the lid on it. Imagine it's 14.7 psi, just like the last example we talked about. But now, instead of just being pure dry air, assume 98% of it is dry air, and then the other 2% is from water vapor, or H2O in gas form. So what are the partial pressures of each gas? Well, partial pressures are going to be proportional to the mole fraction. So you can take your total pressure times 98% to get the total or the partial pressure of your dry air. And then do the same thing for your water vapor, do 2% times the total pressure. And then that's going to be your partial pressure from your water vapor. If you add these up, you'll get 14.7, which was the total pressure. The last principle that you need to know if you're going to do psychrometric calculations is saturated steam properties. So what I mean by that is this is the same thing as if you were looking at a steam table when you're dealing with like a boiler steam system, and just knowing the saturated properties between temperature and pressure. So water vapor is in a saturated state where if it were to be cooled at all, or if heat were to be removed from it, then it would start condensing into a liquid. The temperature of it would not go down, it would start phase changing. And then likewise, if the temperature were held constant but the pressure started to increase at all, then it would condense into a liquid. So every temperature of water vapor has an associated water saturated vapor pressure. And they're correlated. So as temperature increases, your saturated vapor pressure also increases. And then you can, rather than relying on steam tables and looking up saturated properties based on temperature and pressure, there are some equations that we can use to closely estimate this relationship. This is a much better visual representation of what I was just trying to talk about. So here's a typical steam table that you might use for reference. You might look up, okay, if I've got steam at some pressure, what temperature is it at if I'm saturated? Or vice versa. If I know my temperature, what pressure must it be at? Here's a good visualization of the saturation curve I'm talking about. So if you've got temperature on your x-axis, pressure on your y-axis, you exist as steam in this region. And then if you were to cool that steam, let's say you're starting here and you're to cool the steam, eventually you hit your saturation curve here. So at your saturation curve, if you were to remove any heat from that steam, or if you were to decrease the temperature at all and move left, you'd start condensing into water. Or if you were to keep temperature constant and you were to increase your pressure, you'd condense to water. This is the saturation curve that we're going to be dealing with for psychrometrics. We're not really going to be talking about turning it into ice or anything like that. But we will be looking at, for the equations, this curve has a set of equations, and you get to this point, and then that curve is going to have its own curve fit equations. And those look like this. They're very messy and long, but they're embedded in the macros in our Excel workbook, so you don't really have to worry about it. But basically from negative 148 to 32 Fahrenheit, that's where this equation is supposed to be accurate. But I mean, realistically, if you were to go a little bit below negative 148, it still works pretty well. This is the equation, though. It's messy because you've got your natural log of pressure is equal to all these coefficients times an absolute temperature times natural log of a temperature. And what you can do is just take the E or the exp to each side, and then you're left with pressure equals E to this long string of equation. Same thing down here. So from 32 up to 392 Fahrenheit, you can apply this equation. Again, this works pretty well above 392. I think ASHRAE just says that this is the range where it's most accurate. Above that temperature, maybe take some caution that you may not be as accurate, but again, I think it works pretty well after cross-checking with steam tables. So one last thing to add here, there might be an equation where you can calculate your saturated temperature as a function of pressure. I don't have that. What I do in my macros is I have this equation where I can get pressure as a function of temperature. And then if I want the reverse, where I want temperature as a function of pressure, I just have a little root finding algorithm where I basically I change P until T is satisfied. All right, so now let's go and talk about all the different psychrometric properties that we are interested in, and then how we can derive those functions if you know some of the other values. Starting with pressure, I think most people know what pressure is. You can think of it as how hard a gas pushes against the walls of the container, and that's measured in force per area. We usually do pounds force per square inch. But as long as it's a force per area, then it's a pressure. So it could be pounds per square foot, kPa, which is 1,000 newtons per square meter, etc. So pressure gauges read gauge pressure, and gauge pressure is always calibrated to atmospheric pressure, such that at atmospheric pressure, your gauge will read 0 psi. That's not absolute pressure. Absolute pressure is like, what is the actual pressure of the gas, which is atmospheric pressure plus gauge pressure, and that's absolute. Anytime you're doing calculations with, say, ideal gas law or looking up properties in a table, you're always going to use absolute pressure. Anytime you're in the field looking at a pressure gauge or looking at like an HMI screen that says pressure, That's going to give you gauge pressure. So you always have to convert from gauge to absolute before doing calculations. Like I just said, absolute pressure is gauge plus atmospheric pressure. It's typically 14.7, but depending on the elevation you're at, that can change. And that's what this equation here shows. We have this as one of our built-in functions in our macros here. But your atmospheric pressure is going to be your atmospheric pressure at sea level, which is 14.696 psi, times this is your conversion factor, which is a function of your feet of elevation. So if you type in your feet above sea level here into this equation, then you will get this is your correction factor. If you multiply it by your sea level pressure, you'll get your actual atmospheric pressure. All right, let's talk about temperature real quick. Anytime we just say temperature, we're referring to dry bulb temperature most of the time. If you just hear temperature, you're referring to dry bulb temperature, which is the temperature that a dry thermometer reads. That's why they call it dry bulb, because the bulb that does the measurement is literally dry. On your psychrometric chart, it's going to be your x-axis here. And we obviously use Fahrenheit in imperial units or Celsius in metric. A lot of times, if you're doing calculations, like for ideal gas law, you've got to do absolute temperature. So for absolute scale temperature, you got to add 460 to Fahrenheit to get in Rankine, which is the equivalent of like adding 273 to Celsius to be in Kelvin. So always use absolute temperature in ideal gas law. If you're ever working with temperature differences, if like a delta T, it doesn't matter what units you're in because that 460 is going to cancel off. A delta Rankine is going to be the same thing as delta Fahrenheit. That's not necessarily the case. That is not the case, though, going from a delta Celsius to a delta Fahrenheit. You've got to do your conversions from that. Let's talk density real quick. Printing this PowerPoint to PDF made this symbol show up really weird. That's supposed to be rho. Density is that's a weird looking rho, but anyways, density is typically written as the Greek symbol rho, which is your ratio of mass to volume of something. I think everyone knows this, but what's useful to point out is that if you're using your ideal gas law equation, you can substitute instead of m over v, instead of mass over volume, you can do P pressure divided by R times T. That's really useful, so you're not having to look up density in a lookup table or something. You can just take pressure divided by your gas constant times temperature, and that gives you density. If we're doing density for an air and vapor mixture, you would calculate it just like I said, do P over RT for each component. Let me back up a step. Your total air density is going to be your total mass, so the mass of dry air plus your mass of water vapor divided by your total volume. And then since they both gases will occupy the volume that they're in, they'll have a common denominator. So you can just simply add the densities of each one as a function of their partial pressures. So if you know your partial pressure of each one, you can find the density of each one, and then you just simply add the densities together to get your total air density. It's useful to know the total air density because if you have a total CFM of air, you can take your total CFM times the density, and then that'll get your total air mass flow. And we'll dive into examples of that later. Let's talk dew point next. As you cool down air at a given state, it eventually hits the saturation curve, and that point, that temperature at which it's saturated, is called the dew point. That's the easiest way to visually explain it. So for a more technical explanation, you can say that your dew point of your air, your dew point temperature, is your saturated temperature based on the partial pressure of your air vapor mixture. So in other words, let's say I've got air at some state here on my psychrometric chart, if I were to find what the partial pressure of my water vapor is at that point, my corresponding saturated steam temperature for that partial pressure is equal to my dew point. That might be kind of difficult to, it's a kind of a mouthful and hard to understand maybe, but if you do an example or two, once we start looking at the equations, it might make more sense. And what's cool is that this applies to any type of gas mixture. You can apply this to any gas, not just water vapor, but you can do this for anything else. And you don't just have to look at it for dry air and water vapor. So you can do this same thing with a boiler stack that has water vapor in it. If you want to find the dew point, so like if you wanted to look at a condensing stack economizer and you want to know the dew point of the water vapor in that stack, if you know the partial pressure of water vapor in your products of combustion stack, which you can get because you can find what percent of that gas stack leaving is water vapor. So if you know your partial pressure of water vapor and look up its corresponding saturated steam temperature, that would be the dew point of your boiler stack. So generally, when you've got boiler stack products of combustion, and this will depend on the exact components of the flue gas, but generally your water vapor is going to be something like 16 to 18% by mole, which means that the partial pressure of water vapor in those products of combustion are going to be something like 2.5 to 2.6 psi absolute. And if you look at the corresponding saturated steam temperature for that 2.6 psi, that is about 135 degrees or so, plus or minus a couple depending on your conditions. So that's why if you've ever heard that the dew point of water vapor in a boiler stack is about 135 or 133, that's exactly where that comes from. It comes from the saturated steam temperature based on the partial pressure of water vapor in that mixture. Let's do an example again. Let's say we take that same sample of air from the box that's a cubic foot. So our dry air partial pressure is 14 point whatever that is, and the vapor pressure is this, so that they sum up to 14.7. This is our temperature. What's the dew point? So we would take this pressure of this partial pressure of water vapor and find the corresponding saturated steam temperature in a steam table, or we'd use the equations that we saw on the other sheet, and we'd find that our saturated vapor pressure is 63.8, so that's the dew point. The temperature is 70, but its dew point 63.8. So that means that if we were to start cooling down the air in that box, once it hits this temperature, you're going to start getting drops of liquid. All right, now let's take that same sample, but instead of it starting at 70 degrees, let's say it's 105 degrees. So now what's the dew point? Well, what we would do is find the partial pressure of water vapor, which is the same, find the corresponding steam temperature on the steam table, or we'd plug it into that function, and we would find that the saturated temperature for that pressure is 63.8. So what does that mean? It means the dew point did not change. So the point of changing up the temperature here is to show that the dew point is a function of the water vapor pressure. It is not a function of the temperature. So as you heat up and cool down your air, the amount of water vapor in the air stays the same, so the partial pressure of it stays the same, as long as you're not hitting that dew point and dropping water vapor out, or liquid water out. So that's dew point is constant as you heat up and cool the air. It is only a function of the amount of water vapor in the air, or the partial pressure of water vapor in that air. Let's talk next about relative humidity. This is something that it's measured a lot and it's referred to a lot. When people talk about the humidity, it's 50% humidity outside. They're probably talking about relative humidity. So what that is the amount of humidity in the air relative to the vapor carrying capacity of that air. That's kind of a straightforward way of saying it. There's a more technical definition we'll see in a second. So it's expressed as a percentage, and the way I think of that is it's basically what percent full of moisture am I? It doesn't directly tell you how much moisture is in the air. It tells you what percent full we are. So if you're looking at a psych chart, one way to visualize it is if you were to, again, pick a random point. So if I'm here, and then draw a line vertically upward until you hit saturation. Take the entire length of that line divided by the length of the line from your point down to here. The ratio of those two lines is going to be your relative humidity, pretty much. Now, the more technical definition, your relative humidity is your partial pressure of water vapor to the pressure of saturated vapor based on the temperature you're at. Let me say that again. Relative humidity is the ratio of your partial pressure of water vapor to your saturated pressure as a function of your air temperature. So what this means is that unlike dew point, where with dew point as temperature changes, doesn't matter, your dew point stays the same. Here, if temperature increases, your corresponding saturation pressure also increases. So if the denominator increases, then your relative humidity would decrease. So what I just said is that as your air temperature increases, relative humidity decreases. And that makes sense because as your air temperature increases, the amount of moisture that it can hold will increase. So that means your relative humidity would go down. Let's talk humidity ratio. It is the ratio of your pounds of moisture to pound of dry air. It is not the ratio of mass of moisture to total mass. It is the mass of water vapor divided by mass of dry air. Another thing, it's often used interchangeably with absolute humidity. That's technically a little bit different. Absolute humidity is the ratio of water vapor to volume of air. I see this used interchangeably all the time. So if you do, it's not the end of the world, but I would just use humidity ratio to be safe if you're talking about pounds of vapor divided by pounds of dry air. If you ever see the Greek symbol omega, that's when you're dealing with psychrometrics, that's referring to humidity ratio. And it's usually in pounds per pound or pounds per pound or kilogram per kilogram, which would be the same thing because it's unitless. Whenever you see omega, that's typically what it's talking about. What we'll typically use is grains per pound. So a grain is 7,000, or sorry, there's 7,000 grains in 1 pound mass. So if you take your humidity ratio in pounds per pound, or pounds of water vapor per pound of dry air, times 7,000, then you'll be in grains per pound. For a quick number example, if you've got 99 pounds of dry air and 1 pound of water vapor, the humidity ratio would be 1/99. Here's the same thing in equation form. Again, now sorry to beat this horse to death, but it's pounds of water vapor per pound of dry air. And if we were to rearrange this by substituting in PV over RT from our ideal gas law equation, we can write that out for each component of our mixture for vapor and dry air. And you'll notice that for gases, which occupy the space of their container, V is going to be the same for both the water vapor and the dry air. So when you plug these, you substitute these terms in for our humidity ratio definition, it looks like this, and then V cancels out because, again, they occupy the same volume. T cancels out as well because they're going to be at the same temperature. What you're left with is humidity ratio is equal to partial pressure of your water vapor, and I'll say it like this, it's partial pressure of water vapor divided by R for water vapor times R for dry air divided by partial pressure of dry air. So it's PR over PR. And now remember that your specific gas constant is equal to universal gas constant divided by molar mass. So if we make that substitution in here, we can cancel out universal gas constant and then be left with the molar mass ratio. So the final thing you're left with is that humidity ratio is equal to partial pressure of water vapor divided by partial pressure of dry air times molar mass of water vapor divided by molar mass of dry air. And if you're looking at the functions and you ever see like I think it's 0.602 or something like that, that's simply what this ratio is. All that's to say, if we know humidity ratio, we can solve for the partial pressure of water vapor. You've seen that that's come up previously a lot. And you can see here that if you know humidity ratio, you can solve for that, and then that can be used for all the other functions we just talked about. To find it, you can basically expand this by substituting in our total pressure minus partial pressure of vapor for the dry air one. And then you're left with this. It's a little messy looking, but it's straightforward. Still on humidity ratio, but we're going to talk saturated humidity ratio here. So again, when air is saturated, you can no longer hold any humidity in the air. So the temperature and the total pressure are what determine how much vapor can be held by a given air temperature. So if you wanted to find, okay, given a temperature, what is the max amount of humidity ratio I can have for that? If you were to just draw a line vertically up until you hit that saturation curve, whatever that value on the y-axis is your saturated humidity ratio for that temperature. The way you can find that with equations is you know that your saturated vapor pressure is a function of your temperature that you're at by looking it up in a steam table. So if I just take the temperature that I'm at and find my saturated vapor pressure, I can plug that into my partial pressure of water vapor from my humidity ratio equation, and then you're left with something like this. This is the same equation that we were just looking at here, but instead of looking at the actual partial pressure, you're plugging in your saturated vapor pressure as a function of the temperature you're at. So you're left with this guy. All this is saying is that if you know your temperature and the total pressure for your air, then you can calculate the maximum amount of humidity ratio that that air could have. Let's talk about enthalpy next. The definition of it is internal energy plus the product of pressure and volume, which is U plus PV. And what it effectively represents is the energy content of a gas flowing into or out of a control volume. It doesn't account for kinetic energy or potential energy, but those are often neglected with gases anyway. So you can think of enthalpy kind of as the energy content of a substance. Now that enthalpy value itself is not really useful. So like if I say my air is 28 BTUs per pound, that doesn't really tell you anything. But if you take the enthalpy difference from one state to another, that is very useful because it tells you how much energy it gained or gave away. So if you look at your delta of energy from state 1 to 2, you can just take your enthalpy difference. We often look at enthalpy like on the psych chart, or what our macros are going to do is it is in BTU per pound. So it's specific enthalpy. You have to do mass times the specific enthalpy to get your total energy. Now what we do to calculate enthalpy in our functions is, let me go back and look at this equation again. You can also write this as your change in energy is mass flow times specific heat times your delta T, or temperature difference. So what we do to calculate enthalpy is we can simply estimate it as enthalpy is equal to specific heat, or CP, times T. That applies to dry air. You can simply do CP times T to get your enthalpy. For water vapor, we make it a little bit more complicated because we want to account for it being in a gas state. So what you do is CP times T plus, we do plus 1061, and that represents the difference of its enthalpy when it's in a gas state versus a liquid state. So CP times T plus 1061 is how we get our vapor enthalpy. So for our imperial units, what we use all the time, we use 0.24 for the specific heat of dry air times temperature. And you can just do times temperature in degrees Fahrenheit because, like I said, we're typically doing enthalpy differences. So if you're doing an enthalpy difference, it would be the same thing as saying CP times delta T. And you could just substitute that in for H. So then your delta H would be the same as CP delta T if you did this. For water vapor, specific heat's about 0.444 BTUs per pound F. Do that times the temperature it's at, plus 1061 when it's in vapor state. If it was in liquid state, then this would be different. Now, let's say we've got a mixture of dry air and water vapor, which is what we always have. If we wanted to find the enthalpy of it, what you do is find the total enthalpy of that mixture, or the total energy of that mixture, by doing your mass of dry air times your dry air enthalpy, which is this, plus your mass of water vapor times your water vapor enthalpy. And then rather than dividing that by the total mass, we're going to divide that by the mass of dry air only. And we'll talk about the advantages to doing it that way. Technically, you could divide it by the total mass, and what you could do is just call that, enthalpy total as opposed to enthalpy dry or something like that. But what we're always going to do is divide it by the mass of dry air. And that has a lot of advantages when you're dealing with phase changing or evaporating water into a mixture. It simplifies our calculations a lot. You could do it the other way, dividing by total air, but the equations get more complicated and it just gets messy and busier. So if we take this equation and we break it out, so we divide this term by the dry air, divide this term by the mass of dry air, you're left with this. Enthalpy of your air mixture is equal to your enthalpy of the dry air plus enthalpy of water vapor times mass of water vapor divided by mass of dry air. And you might recognize this from a few minutes ago. That is simply humidity ratio. So you can say your air enthalpy is going to be your dry air enthalpy plus humidity ratio times water vapor enthalpy. And if you wanted to write this out with the units that we use, here's our final equation. Enthalpy of our air is going to be 0.24 times T plus humidity ratio, unitless humidity ratio, times 0.444 times T plus 1061. If you wanted to use grains per pound, just divide this term here by 7,000 and you're good to go. Last one we're going to talk about is wet bulb. Wet bulb's the most complicated one to calculate, so that's why we saved it for last. What it technically is, wet bulb is if you were to take a wet paper towel and then wrap it around the bulb of a thermometer and then start swinging it around, that thermometer would read the wet bulb temperature. So what that is wet bulb is the temperature the air can be cooled down by evaporating water into it. Picture you've got this long tunnel that air is flowing through, and it's got some water in it, and this is like infinitely long. So as the air flows through it, water vapor or water is going to evaporate as water vapor into that air mixture. And then by the time it leaves that super duper long tunnel, your air is at a different temperature and a different humidity ratio. Well, it gets to the point where the air becomes saturated and you can no longer evaporate any water into it. That's why it comes out as the saturated humidity ratio. Now, while that water is evaporating into it, we have a constant energy process here, an adiabatic process. So as the water gains humidity ratio, in order for it to not gain enthalpy, it has to decrease its temperature. So you get a 1-for-1 trade-off of gaining water vapor while losing temperature such that your enthalpy stays constant. If you were to do that process for the length of this tunnel, your air would exit at the wet bulb temperature. That's how you can think of it, and that's how I thought of it when I set up the equations to calculate wet bulb. What we're going to do next is write this process out in equation form so that we can talk about it more analytically rather than theoretically. What we said is that as your air is going through that tunnel, it's liquid water is evaporating into that air, and when that happens, the humidity ratio of the air increases and the temperature of the air decreases. Anytime you have a temperature change of a substance, that's called sensible heat transfer because the temperature changes. And if you have phase change occurring, like liquid evaporating into water, you have latent heat occurring. And what we're saying for this process is that the sensible heat loss from the air is going to be equal to the latent heat gained by the air. So let's write out each of those equations. Sensible heat is going to be mc delta T, so mass times specific heat times temperature difference. We're going to assume that we've got 1 pound of dry air for this process, and you'll see why that's convenient in a second. If we've got 1 pound of dry air, then we can just leave that mass term off. So there should be an m here, which is 1. So times Cp of air times delta T. Delta T is going to be the temperature you start at minus the wet bulb temperature, which is what you end up at, and which is what we're trying to ultimately calculate. Plus, I have humidity ratio written here. If you've got 1 pound of dry air, then your pounds of water vapor per pound of dry air is going to be, which is the humidity ratio, is going to be equal to the mass of water vapor. So we're going to say that HR, again, which is the same thing as water vapor mass times specific heat of water vapor times delta T. Our latent heat, which is the heat that is going to be absorbed by the airstream due to liquid water evaporating into it, that's going to be equal to the mass of water that got evaporated times the enthalpy of its gas state minus its enthalpy as a liquid state. So the enthalpy as a gas state is something we've already talked about, specific heat times temperature plus 1061. We're going to use wet bulb temperature because you can assume that's what the temperature of the liquid water in that made-up tunnel is, minus the enthalpy of that liquid. And we can, for a liquid water, we can write the enthalpy as temperature minus 32. And we do that because we use 32 degrees Fahrenheit as a reference point where H equals 0. And since the specific heat of liquid water is 1 BTU per pound F, we can simply write that the enthalpy of liquid water is temperature minus 32. So this is enthalpy of the liquid water, this is enthalpy of the gas, and then this is the mass of water that got evaporated. Okay, and then we can further simplify this into this equation here by taking the difference of these two terms. So we get mass of water evaporated times 1093 minus 0.556 times temperature. You may see this elsewhere as an equation for latent heat of water as a function of its temperature. And then we're also going to write that the mass of evaporated water is going to be equal to our saturated humidity ratio minus our actual humidity ratio. Again, it's 1 pound of dry air, so you can substitute humidity ratio as water vapor mass. So we know we end up saturated, and we start out at some humidity ratio, which we're just going to call HR. we're going to take those two equations that we just wrote and set them equal to each other. And remember from earlier, we've talked about saturated humidity ratio. That is going to be your saturated vapor pressure as a function of your wet bulb temperature divided by the pressure of dry air times your molar mass ratio. This is an equation that we looked at earlier, so we can just substitute this whole term in for HR sat. And when you do that, what you'll find is you've got one equation with one unknown, which is your T wet bulb. That's what you're trying to solve for. But no matter how much algebra you do, you cannot explicitly solve for that. So what that means is that you've got to do some kind of numerical method to solve for it. What I do is take this entire term and subtract it over to this side and set it equal to 0. And when you've got some equation equal to 0, you can do a root finding algorithm where you basically guess different values for this until the equation is satisfied. And once it's satisfied, you know what the correct value was. And that's going to be how you calculate all the psychrometric functions with these equations. So what we can do now is talk about how do these apply to real processes and real equipment. So generally, we know the total pressure of the air. Well, that's typically not something that we're trying to solve for. That's almost always a given. So if you know that, and then any other two variables that we just talked about, we can calculate all of the other psychrometric properties. So we can do that with all the equations we just talked about. If you're going to do it by hand every time, it would be just as tedious as looking it up in a chart. So we've made some macros that do these for us. And we can go into those in a different lesson, but just know that there are macros that will calculate any property as a function of any other two properties. Here's where this comes up a lot, is HVAC is a big one. Cooling towers require psychrometrics because your wet bulb temperature outside is often a control point. That's the theoretical limit you can cool your water down to. Talk about it with compressed air itself a lot. That pressurized air is going to have some dew point requirements or maybe some parts per million water vapor requirements. Doing these equations that we've talked about helps you do that analysis. Not only compressed air, but we can talk about other inert gases, like if a plant's using compressed nitrogen or CO2. Again, we can use the lessons that we talked about to do analysis on those. And then we already talked about products of combustion from a boiler stack and how to find the dew point of water vapor in it. Or there may be other properties of that gas that you may want to look at calculating. And you can apply these same equations to any gas mixture is the point. So let's do an example here. If we know our total airflow, so this might come up if we have a fan curve and we know how much volume of air a fan can push, or if we've got an anemometer where we can physically measure the velocity of air. Well, your volumetric flow rate is going to be the cross-sectional area times velocity. So we can measure area, we can measure velocity, therefore we can measure the actual volumetric flow rate. And if we want to know the mass flow, which is not possible to directly measure, you can calculate it with volumetric flow times density. And like we said earlier, if you know pressure and temperature of a gas, then you can calculate its density. So let's do an example. This looks messy, but it's not that complicated. We can talk through it, or you can pause or something. But let's say you've got a 24 by 16 duct, and you use your anemometer and you measure the velocity at 300 feet a minute. And the air is at standard atmospheric pressure, and it's 90 degrees. We know relative humidity from a tool where we can measure it. There's a lot of ways to measure relative humidity with tools out there. And let's say we say it's 40%. So what's the mass flow of the airstream? If I were just given these conditions at first and I was told to find the mass flow, gosh, my initial reaction is I have no idea. But you can put these equations together and find it. So we know volumetric flow is area times velocity. So let's find our area, convert it to square feet so we can multiply by feet per minute of velocity, and we get 800 CFM. Cool. So we've got 800 CFM, and that's not going to tell you the mass flow rate directly because we don't know the density of it. Well, we can find the density if we know our partial pressures of our dry air and our water vapor, because we can use that ideal gas law to find density is P over RT. What we do know about the humidity in the air is that it's 40% relative humidity. So what does that mean? That means that we're 40% saturated at 90 degrees Fahrenheit, which means the actual partial pressure of our water vapor in this air is 40% of the saturated pressure at 90 Fahrenheit. So let's use our equations to translate what I just said there. We can use our equations from the other sheet to find that that is equivalent to 84.4 grains per pound. And if you know humidity ratio, you can calculate partial pressure. So our partial pressure of water vapor is going to be equal to our total pressure times humidity ratio times this molar mass ratio. I'm not going to say all these terms. Eventually, you find that our water vapor itself is at 0.279 psia. Take 14.7, which is the total pressure, minus that from our Dalton's law. We know that difference would be our dry air partial pressure. With that, you can find your density of dry air and water vapor, and then simply add them together to get the total air density. And when you add the densities together, you wind up with a density of, that should be 0.0716. Sorry, that's my typo. That is 0.0716. If you take your 800 CFM times 0.0716, you should get 56.67 pounds per minute, and that's about 3,400 pounds an hour. So sorry for the typo there. There should be a 0.0716, but you do end up getting this mass flow rate. All right, so with that same thing that we just did, what is the mass flow rate of the dry air only? So here's our total mass flow. What is the dry air mass flow? Well, if you do some arithmetic, you can say that your total mass flow is equal to the mass of dry air plus the water vapor mass. And do some rearranging, and you'll find that your dry air mass is equal to this equation right here, total divided by 1 plus humidity ratio. If you do that, make sure you convert grains per pound to pounds per pound, and then you end up with this number. Your mass flow of dry air is going to be pretty darn close to your total mass flow, just because the mass of water vapor is not going to be very high. Therefore, if you take that difference, you'll find what your water vapor mass flow is. Let's talk now that we know how to calculate dry air mass flow, we can start talking about the energy change that's carried out in an HVAC process. So if you're either cool or heat air, the total heat transfer is going to be equal to your mass flow of dry air times your enthalpy difference from 0.1 to 0.2. If there's any condensation that occurs as you're cooling air, then the energy from phase change is called latent heat. The energy transfer that occurs due to temperature change is called the sensible heat. And if you add them up, you find your total heat transfer. So this here is total heat transfer. Anytime you do mass flow times enthalpy difference, you're getting total. That does not tell you your sensible versus latent heat breakdown. To do that, you've got to look at your humidity ratios before and after. So let's do that. Let's say we've got that same set of conditions of airflow, and we want to cool it down to 55 degrees. That's a pretty common supply air temperature with HVAC. So we know our dry air mass flow because we calculated that. Let's find our enthalpy difference. The reason earlier I said you've got to know if you have any phase changing that occurs is because your enthalpy is going to be a function of your temperature and humidity ratio. If condensation occurs, your humidity ratio will go down. So you need to know what that final humidity ratio is in order to get that final enthalpy. So our starting enthalpy, if we do it in long equation form, we would get 34.9 BTUs per pound of dry air. This can also be done with our macros, but this is what that macro is doing behind the scenes. We know that the final temperature is going to be 55. What's our final humidity ratio? Well, if you're just cooling the air, the humidity ratio doesn't change until or unless you hit the dew point temperature. What's the dew point of our initial air? If the temperature of the final air is less than the dew point, then that means condensation would have had to occur. Otherwise, if there's no condensation, then humidity ratio is going to stay constant. So let's take a look at that. We know that at 90 F, 84.4 grains per pound, our dew point is 62.5. We could do that the long way with looking at saturated vapor pressure as a function of temperature and all that, but we're just going to assume we plugged this into our macro, which is what I did. So the final temperature of 55 is less than this. So what that means is there would have to be condensation that occurs to get past this temperature down to 55. So if you're on a psychrometric chart, if you cool air down to that dew point, any more cooling, you're going to basically just ride that saturation curve down. So what that means is that your final air conditions at 55 are going to be saturated, and saturated means 100% relative humidity. So if I were to find my HR sat, which we talked about earlier, at 55, that corresponds to a humidity ratio of 64.4 grains per pound. So now that we know this, we can find the enthalpy in the final state. So if we do our long equation, which is what the macro does behind the scenes, we would get 23.19 BTUs per pound. So our total heat transfer from this initial state to that final state is going to be 39,306, which is going to be something like 3.2 tons of cooling. Now, there are a lot of quick rules of thumb calculators out there for getting your total heat transfer and then sensible and latent heat. And they're really useful for quick calcs. It will get you into the ballpark, but I think it's important to know where these come from and how they're derived. So this sensible heat transfer equation, maybe you've seen before, but it's 1.08 times CFM times delta T. That's an estimate for your sensible heat transfer. What this assumes, though, is that 1.08 is going to be what allows you to convert from CFM to mass flow times specific heat. And what goes into this constant value here is assuming that you are completely dry, so a zero humidity ratio, and it assumes that your density is at standard conditions, so 0.075 pounds per cubic feet. If your air is hot or very cold, then the density is going to be different than standard air conditions. So that makes the 1.08 inaccurate. And also, if you've got humid air where your humidity ratio is relatively high, then your 1.08 is also not going to be accurate. So that's a word of caution there. The more humid you are and the further your temperatures are away from standard conditions, which is 68 F and 14.7 psi, the less accurate this equation is going to be. Typically, you're going to undershoot what your sensible heat actually is because this 1.08 should be a little bit higher to account for the water vapor that changes temperature in that process. Latent heat's estimated by 0.68 times CFM times your change in grains per pound. That's a pretty decent estimate. If you know your grains per pound humidity ratio before and after your process, this generally gives you a decent estimate. I've also seen 0.7 as your constant factor here, and that works fine. The other one here, 4.5 times CFM times your enthalpy difference gives you your total heat transfer. Again, the only issue here is this 4.5 is assuming your air density is the density at standard air conditions. So the further you are away from 68F, the less accurate this becomes. Generally, I think these are decent estimates. I think that Q total and Q latent are decent, sensible. Again, it's fine to use. It's pretty accurate, but that's going to be the least accurate compared to these two from what I've found. Let's talk about one example where this is applied is in humidity controls. So dehumidification is required a lot in spaces that have tight humidity controls. That if you've got a requirement for outside air, which may be moist at times, you're going to have to dehumidify it. And it's difficult to just go from point A to point B on a psych chart where point B has a lower humidity ratio. A typical process is you got to take a bit of a detour. You have to cool the air all the way down to the dew point, ride that saturation curve. And now, once you've ridden the saturation curve down, you can hit your humidity ratio that's required. But sometimes by the time you're at that humidity ratio and you're saturated, that air is too cold. And if it's saturated, there's oftentimes dew and liquid water that might get infiltrated into the space, which can cause mold issues and stuff. So you often reheat that air, and you'll reheat it to some temperature that's comfortable to put into the space. So that's a typical way dehumidification is done. Now, what you'll do is if you say, I want my supply air to have some humidity ratio, you can say, okay, that corresponds to some dew point. So if I always cool my air down to this dew point here, or this temperature, which corresponds to a dew point, as long as I'm at that temperature, I'm going to be at the humidity ratio that's required. That's the easiest and laziest way to set the controls up. Now, here's the problem with that. What happens if the air is already dry enough and it didn't need to be dehumidified? Here's what you're going to do. If this orange is the typical process where you have to dehumidify down here, what if instead of starting at this orange point, you're starting at this red point? Your controls are saying, okay, cool down to this dew point no matter what. Okay, so I cooled down to there. Now I'm at this temperature, I'm at 50 degrees. But guess what? My humidity ratio didn't change, so I did not dehumidify that air at all because it didn't need to be. So now what do? My controls say to reheat that air to a comfortable temperature. Well, guess what? I just cooled my air down to this point, and after you're here, you're just cooling it and reheating it for no reason. So that's energy waste that can be avoided if your controls are smart and can look at your entering air conditions and whether you need to dehumidify or not. You can avoid that waste where you're constantly excessively cooling and then excessively reheating that air. So when your controls are set up that way that I described, it leads to energy waste. It's a little bit dramatic, but it's true. It is wasted energy when the air is already dry enough. So like I said, the better control scheme is to look at your air starting conditions versus your final conditions and say, okay, is my dehumidification needed? If not, then just cool it down to the supply air temperature directly. Don't overcool it and then reheat it. We sometimes call that flip-flop control, where you flip and flop between dehumidification mode or just cooling mode. So some other processes that use psychrometric analysis are cooling towers, like I said, the outside or the water that you can cool your water down to is limited by your outside wet bulb temperature. So you can use wet bulb as a point to control your fan energy and optimize it. That way you're not just running your fan at 100% speed trying to achieve a temperature that's unachievable as a function of your wet bulb outside. So if you look at your wet bulb temperature, you might say, I can never get my water temperature down as cold as I'd like, so I can just slow my fan down and get the same results as if it were running at 100%. So a lot of words there to just say that you can look at wet bulb to optimize fan energy. Compressed air is not something you often think about using psychrometrics for, but dew point and moisture content of compressed air is important. And if you're going to do any type of detailed analysis on that, you end up doing psychrometric calculations to look at dew point and humidity ratio of that air. I've had some projects too where we're looking at installing a PSA or pressure swing adsorption nitrogen system, where instead of buying liquid nitrogen, which is expensive, a site may be able to generate nitrogen gas with some equipment. And one of the things that they run into, or that you have to do in sizing or designing a PSA nitrogen system, is look at the moisture requirements in that air. And they don't often say, this is the humidity ratio or dew point. They'll give you a spec in parts per million of water vapor or ppm. And it's often, the requirements are that it's very dry. So doing any kind of analysis on ultra dry nitrogen or other inert gases, you can use these same equations and psychrometric principles that we talked about to figure out how to achieve those conditions and what your drying requirements might be to achieve that. All right, that's it. Hopefully that helps. And if you've got any questions, feel free to reach out. If you're interested in looking at the macros and how those are built and how they work, let's talk about that next. But let me know if that would be of use.